Welcome to G Fun Facts Online. Imagine a symphony orchestra where every musician is blindfolded and wearing noise-canceling headphones. At the conductor's initial downbeat, they all begin playing in perfect unison. For a few fleeting moments, the music is a flawless, complex masterpiece. But as the seconds tick by, without the ability to synchronize with one another or the environment, a violinist drifts out of tempo. A cellist misjudges a rest. The brass section falls behind. Within minutes, the intricate symphony dissolves into a chaotic, irrecoverable cacophony of noise. In the realm of quantum mechanics, this descent from perfect harmony to random static is known as quantum decoherence. For decades, the promise of quantum computing has tantalized scientists. It is a technology that promises to solve computational problems in minutes that would take classical supercomputers millennia to process. By leveraging the bizarre, mind-bending properties of quantum mechanics, namely superposition and entanglement, quantum computers process information in a fundamentally different way than the classical machines we use every day. However, this immense power comes with a debilitating Achilles heel. Quantum information is incredibly fragile. The very states that give quantum bits, or qubits, their unimaginable processing power are highly susceptible to the slightest environmental disturbances. Decoherence is the timer on the quantum bomb. It is the exact rate at which qubits lose their stored quantum information to the surrounding environment. If a qubit decoheres before a calculation is finished, the information is permanently lost, and the output is nothing but randomized errors. Understanding, mitigating, and ultimately defeating quantum decoherence is not just a niche physics problem. It is arguably the single greatest engineering challenge of the 21st century. To truly understand why qubits fall apart, we must first understand how they hold together. Classical computers operate on bits, which are strictly binary. A bit is either a 0 or a 1, akin to a light switch that is either completely off or completely on. A qubit, however, operates on the fluid principles of quantum mechanics. It can exist as a 0, a 1, or any linear combination of the two simultaneously. This state is known as superposition. If a classical bit is a coin sitting flat on a table showing either heads or tails, a qubit in superposition is a coin spinning rapidly in the air. Furthermore, qubits can be entangled. When two or more qubits are entangled, the state of one is intrinsically tied to the state of another, no matter how much physical distance separates them. Measuring one entangled qubit instantly collapses the state of its partner. This property allows quantum computers to perform highly complex, parallel calculations, processing vast probability spaces all at the same time. The maintenance of these delicate states, superposition and entanglement, is called coherence. As long as a quantum system remains coherent, the spinning coins are perfectly synchronized, and the quantum computer can perform its algorithmic magic. But to maintain coherence, a quantum system must be perfectly isolated from the rest of the universe. The moment the quantum system interacts with the classical environment, whether through a stray photon of light, a microscopic fluctuation in temperature, or a faint magnetic field, the environment effectively measures the system. The spinning coin crashes to the table, forcing it to choose a definite state of 0 or 1. The quantum magic vanishes instantly. Quantum decoherence is the bridge between the bizarre quantum realm and the predictable classical world. It perfectly explains why macroscopic objects like chairs, apples, and human beings do not exist in a superposition of states. Mathematically, a quantum state is represented by something called a density matrix. The diagonal elements of this matrix represent the classical probabilities of the system, meaning the likelihood of being in state 0 or state 1. The off-diagonal elements represent the quantum coherences. These are the interference patterns between the states that actually allow for quantum computation to occur. When a qubit interacts with its environment, the two become entangled. This entanglement causes the information about the qubit's delicate state to leak into the surrounding environment. As this information leaks, the off-diagonal terms in the density matrix undergo an exponential decay, rapidly shrinking towards 0. The system loses its quantum interference properties and becomes a classical statistical mixture. The wave function has collapsed. This loss of coherence is quantified by two primary timescales, colloquially known as the dual villains of quantum stability. They are known as T1 and T2. T1, or longitudinal relaxation time, measures the energy loss of a qubit. A qubit typically consists of a ground state, representing 0, and an excited state, representing 1. Like a ball precariously balanced at the very top of a steep hill, a qubit in the excited state naturally wants to release its energy and roll down to the lowest possible energy state. If a qubit is prepared in the 1 state, T1 is the average time it takes for it to spontaneously emit a photon or a phonon into the environment and decay back down to the 0 state. While T1 deals with energy, T2 deals with time and synchronization. T2, or transverse relaxation time, measures exactly how long a qubit can hold its superposition before its phase gets scrambled. Imagine two pendulum clocks swinging in perfect harmony. If a slight, random breeze hits one of the pendulums, its timing will shift. It has not lost energy, as it is still swinging, but it is no longer synchronized with its partner. In a quantum computer, fluctuating magnetic or electrical fields cause the relative phase between the 0 and 1 states to drift randomly. T2 is often the more restrictive bottleneck, as qubits generally lose their phase long before they lose their actual energy. Visualized on a theoretical geometric model called the Bloch sphere, the state of a qubit is a vector pointing from the center of the sphere to its surface. The poles represent classical 0 and 1, while the equator represents equal superpositions. T1 relaxation pulls the vector out of the equator and forces it up toward the North Pole, or the ground state. T2 dephasing acts like a blur, smearing the vector's precise direction around the equator until its phase information is entirely lost to the void. The classical environment is incredibly loud, and it attacks qubits from every conceivable angle. To achieve high coherence times, scientists must isolate qubits from an astonishing array of environmental hazards. The first enemy is thermal fluctuation. Heat is essentially the kinetic vibration of atoms. Even at room temperature, these vibrations contain more than enough thermal energy to violently knock qubits out of their fragile states. This is exactly why many quantum computers, particularly those using superconducting circuits, must be housed in massive dilution refrigerators and cooled to around 15 millikelvins. That is a temperature colder than the vacuum of deep space. The second enemy is electromagnetic interference. Stray magnetic and electrical fields can easily scramble the phase of a qubit, accelerating T2 dephasing. Even the Wi-Fi signals in a laboratory, the magnetic field of the Earth itself, or the faint electrical hum of the building's wiring can cause catastrophic calculation errors. This necessitates extreme, heavy magnetic shielding around the quantum core. The third enemy involves material defects. The physical substrates upon which qubits are manufactured, often highly purified silicon or sapphire, are rarely entirely perfect. Microscopic defects in the crystal lattice can act as two-level systems. These defects behave like parasitic, microscopic sponges that absorb energy from the qubit, rapidly accelerating T1 relaxation. The fourth enemy is control line noise. The ultimate paradox of quantum computing is that to use a qubit, you must communicate with it. Scientists use heavily shielded wires to send microwave pulses down into the fridge to manipulate the qubits. However, these very control lines act as highways for classical noise to travel down into the quantum processor, bringing destruction with them. Finally, the fifth enemy comes from above, in the form of cosmic rays and background radiation. In recent years, researchers discovered a stubborn limit to qubit stability. High-energy cosmic rays from deep space and trace amounts of ambient radioactivity naturally present in building materials occasionally strike the quantum chip. When they do, they shatter chemical bonds in the substrate, releasing a cascade of vibrational energy called phonons that sweeps across the entire chip, destroying the coherence of multiple qubits simultaneously. Because different physical systems experience these decoherence enemies differently, the quantum computing industry is fractured into several competing hardware modalities, each with its own unique strategies for maximizing coherence times. Superconducting qubits, currently used by industry giants like Google and IBM, are printed onto microchips similar to traditional computer circuits. They rely on frictionless electrical currents, operating at near absolute zero. They are incredibly fast, allowing for quick computation, but historically suffered from notoriously short coherence times, often decaying in less than 100 microseconds. Trapped ions, used by companies like NISQ and Quantinuum, take a totally different approach. These systems use complex laser arrays or microwaves to trap individual charged atoms or ions floating in a vacuum chamber. Because they are isolated in a vacuum, they are highly shielded from environmental noise, resulting in inherently longer coherence times that can last for several seconds. However, their gate operations, which is the time it takes to actually perform a calculation, are much slower than superconducting circuits. Neutral atoms are similar to trapped ions, but use uncharged atoms held firmly in place by highly focused lasers known as optical tweezers. They offer excellent coherence and high scalability potential. Photonic qubits use individual particles of light to carry quantum information. Because photons rarely interact with each other or their surrounding environment, they are highly resistant to decoherence and can actually operate at room temperature. The main challenge there lies in forcing them to interact when necessary for logic gates. Finally, there are topological qubits, considered the holy grail of quantum hardware and heavily championed by companies like Microsoft. Topological qubits encode information in the structural layout of quasi-particles. Because the information is stored globally across the structure rather than locally, a local environmental disturbance cannot easily flip the qubit. They are theoretically immune to most forms of decoherence, though practically realizing them remains a monumental physics challenge. For years, the brutal battle against decoherence yielded very slow, incremental progress. However, the years 2025 and 2026 have been widely recognized by industry experts as the definitive turning point for practical reality, unleashing a torrent of massive breakthroughs in qubit stability. We are now witnessing coherence times that were considered pure science fiction just half a decade ago. Let us talk about shattering the transmon millisecond threshold. Superconducting transmon qubits are heavily favored by the industry due to their incredibly fast operation speeds and compatibility with existing semiconductor manufacturing techniques. Their primary disadvantage has always been their short shelf life. However, in July 2025, a brilliant team of physicists from Aalto University in Finland achieved a monumental milestone. They published a transmon qubit measurement with an echo coherence time that hit a maximum of 1 millisecond, with a median of 0.5 milliseconds. This drastically extended the window for error-free operations. Just months later, in November 2025, researchers from Princeton University pushed the boundaries even further. They designed a novel transmon qubit architecture that achieved coherence times of up to 1.6 milliseconds. That is a staggering 15 times longer than the previous industry standard. Because these new, highly stable qubits are fundamentally similar to those used by Google and IBM, they can easily slot right into existing processor designs, bringing large-scale, fault-tolerant quantum systems significantly closer to reality. But while a millisecond is a long time in the quantum world, a Paris-based startup called Alice & Bob completely rewrote the rulebook in September 2025. They announced the creation of the galvanic cat qubit. This is a highly specialized superconducting qubit that resists bit flip errors for an astonishing 33 to 60 minutes. This is millions of times longer than typical superconducting qubits. While running quantum operations at a breakneck speed of 26.5 nanoseconds, the galvanic cat maintained a 94.2% fidelity. By solving the error problem at the source through intrinsic physics, rather than relying purely on software correction, Alice and Bob dramatically simplified the hardware architecture required for future machines, targeting a fault-tolerant system of 100 logical qubits by 2030. Meanwhile, in June 2025, physicists at the University of Oxford targeted the accuracy of the quantum operations themselves. Using trapped calcium ions as qubits, they achieved the most accurate quantum logic operation ever recorded, resulting in an error rate of just 0.00015%, or roughly one error in 6.7 million operations. Crucially, they achieved this by discarding the conventional use of bulky, unstable laser arrays. Instead, they controlled the quantum state using pure electronic microwave signals. This method is not only significantly cheaper and more stable, but it was successfully conducted at room temperature without the need for extensive magnetic shielding, drastically lowering the barrier to scaling up quantum hardware. Furthermore, even highly stable qubits experience sudden microscopic variations in performance over time. In February 2026, researchers at the Niels Bohr Institute pioneered a major breakthrough in exactly how we measure decoherence. Previously, standard testing methods took up to a minute to measure average energy loss, completely masking rapid, real-time qubit fluctuations. Using incredibly fast field-programmable gate array hardware, the teams successfully tracked changes in delicate quantum states 100 times faster than previous methods. They can now instantly monitor the exact fraction of a second when a qubit shifts from a good state to a bad state, allowing for real-time calibration and adaptive control that can course-correct before the system entirely decoheres. But while extending the natural coherence time of a physical qubit is absolutely essential, the laws of physics dictate that we can never isolate a system perfectly. To solve radical challenges in fields like materials, science, cryptography, and medicine, quantum computers will eventually need to perform trillions of continuous operations. If a qubit lasts for 1 millisecond, but an algorithm takes 10 minutes to run, the system must actively fix errors much faster than decoherence can cause them. This brings us to the ultimate shield against decoherence: quantum error correction, or QEC. In classical computing, error correction is remarkably simple. You just copy the data. If you want to make sure a 1 does not accidentally flip to a 0, you simply encode it as 3 ones. If a cosmic ray flips 1 bit so the system reads 101, the computer takes a majority vote, realizes the mistake, and corrects it back to 3 ones. Quantum mechanics entirely forbids this approach. According to a fundamental rule called the no-cloning theorem, it is physically impossible to create an identical copy of an unknown quantum state. If you try to read a qubit to copy it, you instantly collapse its superposition and permanently destroy the data. To bypass this impossible roadblock, QEC relies on the immense power of entanglement. Instead of copying the data, QEC takes the fragile information of a single quantum state and entangles it across a vast web of multiple physical qubits to create one single, highly stable entity called a logical qubit. These secondary physical qubits, known as ancilla qubits, act as a network of sensors. By carefully measuring the parity, or the relative relationships, of the ancilla qubits without directly looking at the core data itself, the quantum computer can perfectly deduce if a bit flip or a phase flip error has occurred. It can then apply a corrective microwave pulse to fix the state before the logical qubit decoheres. The year 2025 marked a definitive paradigm shift in this crucial arena. Experts continuously point to Google's Willow chip, unveiled in late 2024, as the exact moment QEC successfully made the leap from abstract theoretical physics to tangible hardware reality. Google proved that scaling up the number of physical qubits could practically drive down logical error rates. This triggered an absolute QEC code explosion throughout 2025. Between January and October of that year alone, over 120 new peer-reviewed papers on QEC codes were published, marking a massive jump from previous years. Industry consensus firmly solidified around one simple fact: QEC is no longer a futuristic goal. It is the beating heart of the quantum computing industry and the universal priority for utility-scale computation moving forward. Companies like Qwera Computing laid down aggressive, highly achievable roadmaps entirely based on QEC. For 2025, Qwera targeted a model with 30 logical error-corrected qubits, supported by over 3,000 physical qubits, utilizing a fascinating technique called magic state distillation to allow for the execution of highly complex logic gates with incredible fidelity. By 2026, Qwera's third-generation QEC model introduced 100 logical qubits backed by 10,000 physical qubits. This represents a monumental threshold capable of executing deep logical circuits that finally push quantum computation far beyond the simulatability limits of classical supercomputers. Because hardware stabilization and QEC are very heavy, resource-intensive solutions, brilliant researchers have also developed algorithmic techniques and pulse control protocols to outsmart decoherence at the software and microwave control level. One such technique is called dynamical decoupling. This involves hitting the qubit with a continuous, precisely timed sequence of microwave pulses, effectively flipping it back and forth. If a low-frequency environmental noise is slowly dragging the qubit out of phase, flipping the qubit halfway through the noise exposure causes the second half of the exposure to perfectly cancel out the first. It is the exact quantum equivalent of a swimmer swimming upstream against a current for 5 minutes, and then turning around to swim downstream for 5 minutes to end up exactly where they started. Another massive software victory occurred in April 2025, when a research group at the University of Southern California published a landmark paper demonstrating a coherence-stabilized technique that bypassed the traditional Ramsey limit of measurement. By applying continuous, slowly varying microwave control, the team manipulated the vector of the quantum state on the Bloch sphere, intentionally dumping the decoherence into trackable, stabilized directions. This not only enhanced the sensitivity of the qubits for quantum sensing, but drastically sped up the calibration of superconducting devices, allowing processors to maintain high measurement fidelity over much longer periods. Software and algorithmic design also play a vital role in managing this noise. In 2025, Google proudly announced the quantum echoes algorithm. Earlier quantum algorithms were universally bottlenecked by extremely limited stability. Quantum echoes fundamentally redefines how the computer treats algorithmic queries, utilizing far stronger entanglement protocols interwoven with real-time error correction to keep the quantum states perfectly steady for significantly longer periods. This software breakthrough provided highly verifiable evidence of quantum advantage over classical systems, beautifully showcasing that intelligent algorithmic design can effectively hide the fragile computation from environmental noise. For the last decade, the entire industry has existed in what is known as the NISQ era, which stands for Noisy Intermediate Scale Quantum Computing. In the NISQ era, machines possessed enough qubits to be scientifically interesting, but were far too noisy and decoherence-prone to execute deep, world-changing algorithms. The convergence of the massive 2025 and 2026 milestones, including Princeton's 1.6 millisecond transmons, Alice and Bob's incredible hour-long bit flip resilience, the deployment of active logical QEC, and real-time FPGA feedback loops, signals the definitive end of the NISQ era. We are now officially entering the era of fault-tolerant quantum computing, or FTQC. This transition is not merely a fun academic victory, it is currently triggering a massive geopolitical and commercial infrastructure race across the globe. Following these stabilization breakthroughs, sector investment surged by an incredible 50%. Governments around the world recognize that stable utility-scale quantum computing is an absolute strategic imperative. In late 2025, the Canadian government launched the $92 million Canadian Quantum Champions program, projecting that mature quantum technologies could contribute over 3% to their total GDP by the year 2045. The global stakes are astronomically high, with systems bridging the gap toward trillions of error-free operations through real-time correction. The encryption shock timeline is rapidly accelerating. A sufficiently large, highly stable quantum computer running Shor's algorithm will be capable of factoring prime numbers exponentially faster than any classical machine, effectively breaking the RSA encryption that secures the modern internet. Industry analysts now project that highly sensitive data encrypted today could be easily decrypted by stable quantum systems as early as the early 2030s. Yet, the constructive power of coherent qubits vastly outweighs the disruptive potential. When a quantum processor can reliably hold its coherence, it acts as a perfect simulator for the natural world. Modern materials science relies entirely on understanding how electrons behave and interact inside complex solids and molecules. With long-lived logical qubits, we will no longer have to discover new, efficient batteries, room-temperature superconductors, or life-saving pharmaceuticals through decades of tedious trial and error. We will perfectly simulate their exact molecular interactions in a virtual quantum environment, entirely bypassing years of expensive laboratory research. Quantum decoherence, the once seemingly insurmountable barrier that caused wave functions to collapse and calculations to perish into random noise, is finally being tamed by human ingenuity. By perfectly marrying the exquisite isolation of advanced physics, the raw computational heavy lifting of error correction algorithms, and the blinding speed of real-time control hardware, scientists have transformed the fragile quantum state from a fleeting anomaly into a highly stable, industrial powerhouse. The timer on the quantum bomb has finally been paused. The beautiful symphony of the quantum realm is finally playing in perfect, uninterrupted harmony. Thank you for listening to Fun Facts Online.